So I'm super excited about this one, and let's welcome Mircea and Peter on stage, and we'll start with a rolling video of Hitman with maybe some audio. We'll see if it works.
Hi, thank you for having us here. Like Matt said, Mircea and Peter. And if you're not familiar with Hitman, just quickly, it's a stealth-based secret agent fantasy game with a very open sandbox-style gameplay. And yeah, here's a trailer. No audio, but imagine. Okay, you kind of get the idea. At I/O, all of our games are backed by our in-house Glacier engine. And before we dive too deep into the rabbit hole, I want to give you a bit of context about this port, because if you want to feel inspired and maybe use some of our work for yourself, it's good to have this background because we worked under certain limitations. Chief among all of them was the fact that this was mostly an engineering port on the engine side, which meant we have no access to artists to touch up our resources to make them mobile ready or mobile friendly. At the same time, Hitman has been released for a few years now, and at that point we branched off the engine and the game. And we, of course, still fix bugs. We still have live content updates in the form of elusive targets. But it also means that all of the niceties of the newer things that are in G2 are not available to us for this port. You may think of things like maybe a frame graph, which will be really helpful to use for mobile, or just geometry streaming system, so you don't have to preload all of the geometry for a level up front. And finally, while I/O is not a particularly small studio, we do have quite a lot of projects in flight at a given time and quite a lot of platforms, so there's not a lot of people to go around. So we really put a high value on low maintenance cost. So just keep that in mind going forward. Now, a quick primer on mobile. There were some other talks here if you're in the room. If not, here's a speed run for you. What we're mostly talking about is pretty powerful chips in really small form factors, and that basically leads to thermal issues and throttling and all of that jazz. And chief among all of those things is probably memory access. And our friends at ARM give sort of these rough numbers. About 1 watt buys you around 170 megabytes of bandwidth if you're targeting 60 FPS. That's per frame. And you can see from the numbers up there that on the lower end of the spectrum, that could be up to 30% of your total frame budget, so quite constrained. So mobile hardware has evolved in time, and consequently also how we write software for mobile hardware in order to deal with these issues and to pretty much try to save as much bandwidth as possible. Now, where we actually started with this port was by trying our Windows build on Mac hardware, and you can do this with Apple's Metal Game Porting toolkit. And we did this mostly just to get like a sanity check to see if the game runs at all. Are there any big, huge glaring issues? What's the memory budget looking like? And things of that nature. And we landed on this as a min spec, which is pretty high, but pretty much on par with other big games that have been ported to iOS. And that is an iPhone 15 Pro and running iOS 18. And I have to say that for us, the driving factor for this choice was memory. Not features. Feature-wise, we could have gone way back. But the smallest that we ever got Hitman, actually, in terms of footprint, was around 4 gigabytes if we look at the PS4 build or the old PC VR build. But the problem with that is that iOS kind of tries to eat a bunch of memory itself as well. And also, if you have apps open in the background, they also eat a bit of memory. And another fun fact for you, I'm not sure if it's the same for Android, but at least on iOS, you don't have swap, right? So if you're flirting with the memory limits, what the OS will try to do actually is do in-memory compression, and when that thing kicks in, say goodbye performance. iOS 18, we actually were targeting iOS 17 first, but we're going to get to it into the talk a bit later where we moved away from that. And yeah, to the right, you have even these limits, you kind of have to ask for them from the OS. So those are good things to keep in mind if you're trying to make a game. And with that, I'll hand it over to Peter so he can give you an overview of how we render a frame.
Yes, so let's dive straight into it. I want to start out by talking a bit about the kind of threading setup we have in the engine. So we of course have our main thread, which is just dealing with the regular things like gameplay, logic, and loading, and so on. But then we also have our render thread, and that's kind of the way that the engine has been parallelized for now at least. So you have the render thread, which will do all this calling and recalling GPU commands and all that stuff. And the way it works is after a frame runs on the main thread, then you have this reflect step, we call it, where that will copy all the data you need from the main thread onto the render thread, and then they can run in parallel, right, at the cost of a bit more latency. And in addition to that, it also has this configurable extra latency that can be put in, which it's configurable for us, but it kind of doesn't really change for the game. But it does have like an extra frame that can go in there, so if you have a case where the main thread is spiking a bit, then that doesn't actually then end up with you dropping frames. So gives you a little bit more headroom to play with. And then a little extra complication is that these frames, they don't necessarily run one-to-one with display frames. So sometimes we skip presenting a frame for various reasons, and also the kind of owner of a frame is a bit, can change a little bit. During gameplay, generally will start on main thread and then get transferred to render thread. But during loading, for example, our main thread will just go like block in a loop, focus on loading stuff, and then the render thread will actually take over. And actually, we in the iOS port, we ended up with multiple main threads, actually, because a lot of these Apple APIs, they are this event-based thing where you get callbacks for the most part. And that callback is really just, like it's a function that then gets executed on some event loop. And that event loop on the main thread also handles all this stuff like I/O, and there's also some stuff for presentation and so on. So you really don't want to block that thread. It's meant to be used in this, you don't block on things, you register a callback that then gets called later. And that's a little bit of a problem for how our engine is structured, because our main and render threads, they're just made to run their own event loops, essentially. And they will just block in the middle of the loop to get the thing that they're waiting for. And early on, we ran into some issues when just running our main thread on the regular main thread. So we just ended up giving the game its own main thread. And then we have this little setup to allow the two main threads to throw functions at each other and run at their convenience. And moving a bit further to going a bit towards how do we actually then get to present a frame in Metal. You need to do this thing, acquire a drawable. It's Metal term for a back buffer. And Metal has quite a few options available for you here. There's kind of the basic one, it's just this next drawable function you can call. And that will just block you on when there's a back buffer available for you to begin drawing into. And then you also have these display link options, where the first one is, so they're kind of for integrating a bit more with vsync. And at least on iOS, you cannot really get around vsync, but also it is something really wrong in the game for it to run smoothly. And so the first one will just kind of give you a callback on every vblank, and then you figure it out and you call next drawable. And then the other one, this Metal display link, is the kind of fancy option that also deals with some latency handling for you. And that is really the recommended approach, because it also gives you this drawable just as part of your callback. But when you have this kind of slightly complicated threading setup that we have, then we just couldn't find a way to make it work. And at some point, we also noticed that we were kind of dropping frames fairly often. And we noticed when profiling then that we had this issue with quite a lot of variability, and then when we would either get the drawable or get the callback from the display link. And I mean, 2 milliseconds is probably never really good in any case, but it's especially problematic on this hardware because it does this kind of cool thing where if you're targeting 30 FPS, for example, then the GPU is actually just eventually, if you're running at, let's say, 20 milliseconds, it's gonna just downclock the GPU until that frame takes 33 milliseconds, because that saves power and can be used in other places. But then it's pretty bad when you're then suddenly 2 milliseconds late, because then obviously you miss a frame. So what we ended up doing instead is kind of modify our metal backend so that this call to next drawable, actually getting the back buffer, was pushed all the way to the end. So only when we actually had a draw call that literally needs to refer to this thing do we actually call it. And then at that point, we cut everything that we've recorded so far in the command buffer and shove it off to the GPU, and then actually do the blocking call. Because then the GPU actually has something to work with, be it the previous frame or the stuff we submitted early. And then, when we get that thing back, the GPU is hopefully still busy, and then we can submit the rest of the frame. And that's usually just like stuff like some post-processing stuff, which is on the CPU side very quick to encode. So this just gives the whole system a little bit of a wiggle room, and it made it run way, way smoother for us. And going a little bit off of that, also want to talk a little bit about frame pacing, which the concept of this is kind of like your frame should be displaying for the same amount of time on screen. And I've tried to draw it up a little bit here, so you can see like in the first row, there's this GPU line, right? And you can see some frames that they look pretty similar, and I can see I made my lines going through all the way a bit too transparent. But imagine that the lines at the bottom, they kind of extend all the way up. So what's happening here is that because those frames are, even though on average they are probably 30 Hertz frames, then they might oscillate a little bit around the V-blanks, and then you can end up with this situation where stuff is, presenting for 2 frames on screen, then 3 frames, then 2, then 1. And that gives you a lot of stutter, and it makes your FPS not feel like what it actually is. Metal has a pretty easy way to fix this. You can just tell it like, hey, this thing should not be presented before the previous frame has actually been on screen for a certain amount of time. And so here's kind of the full picture of how our frames kind of pipeline its way to the display. And we also have a bit of a kind of handling here for if the display or if the GPU does end up being late with some things, to kind of also feed its way back toward the rest of the system, so that can kind of not skip ahead too far.
Yes. So before we actually get to run the game on iOS, we have to deal with all of the resources that are needed. And in G2, this happens around what we call the resource server, which is an application that can run on all of our dev machines. And it itself can spawn other processes or threads, which we call packers, which are tasked with either partially or fully dealing with one type of resource. So that's basically taking them from authoring formats to runtime formats. This setup is really flexible and nice for us because it also means we can cache these results and distribute them across the network, so it makes dev life a bit easier. And it also comes with the advantage that whenever you get a new platform, you basically just need to add the small packers that are different, and you already have a pretty big setup that's already working for you. And of course, when you ship the game, you basically just put all of those packages with the game files. Now for the iOS, in terms of graphics, we had to deal with 2 major packers. The number 1 was textures. We chose to go with ASDC because we found that it gives a pretty good compression ratio to quality value, and the image is borrowed from NVIDIA, thank you. And it also, ASDC, it's a bit more widespread on mobile hardware, so it's a good choice. The thing is, again, we have no artists to look at this. We're sort of on our own. So there was already a pass through the game in which artists and art directors looked at the textures and basically decided how much we can decimate the textures with BC formats. So what we did in our ASDC packer was just look at what was the BC format associated with a resource, and then chose an ASDC block size that it basically gives us the same or similar compression ratio. And that seemed to work fine. It's also worth noting that here in the texture packer is usually where we would do GPU-specific swizzles if the platform we were targeting supports that, which basically just, if you're not familiar, lets you offline prepare your data to be optimal for GPU reads. Apple doesn't give us that, even though we ask nicely. So maybe if more of us ask, they will eventually do that. And yeah, we do the encoding using ARM's ASDC encoder. Apple provide their own, but it just seems like it's a wrapper around multiple third-party tools, and we already were using this for other things, so we just went with it. The other packer, which is probably more interesting, is shaders, and surprise, we're using HLSL. And yeah, it's pretty vanilla. We have a bit of stuff on top just to be able to express things like techniques, but it's fairly simple. We also have these small snippets that we expose into a visual editor because our artists like to work with that, and those kind of get collated together into a final file at the end. Maybe one thing that's maybe special about our HLSL setup is that we have what we call these declaration files, in which we basically write our const buffers. And this is just so we can run it through a tool that would generate these compatible C++ and HLSL structs, just so we don't have to deal with all the const buffer alignment rules. And also gives us some nice quality of life stuff like named buffer slots and offsets for the members of the struct and so on and so forth. But at the end of the day, we end up with some HLSL source. So we need to get that into a metal lib somehow. And traditionally, you would do something like this, basically take the spear cross route. And I've shipped with this in the past, and it's battle tested and it works, but you can see the pipeline is pretty deep. The code goes through a lot of conversions. And a lot of the niceties that you have in MSL to tackle things that are specific for TBDR architectures and things like frame buffer fetch, they're really not easily expressible in HLSL through this pipeline. So what you would end up doing is probably annotate something and then write a custom tool that after spear cross on the MSL does some magic to fiddle with that. It gets messy really quick. So what we ended up using is Apple's new metal shader converter. We didn't originally start with this because right when we were starting our port, it was only version 1 available, and it was missing quite a lot of debug features. But at a certain point, we switched to because they released version 2 and they fixed all of those. And the nice thing about this, it's a simpler pipeline, and it exposes all of these nice TBDR things. Yeah, and it's for first-party support. And what gave us final confidence to actually go with this, even though there weren't a lot of projects using it at the time, is the fact that you can pretty much mix MSL shaders in pretty easily. So even if we would run into some blocker, we knew we could handcraft something in MSL. So this is at offline stage, but for shaders, we also need to look at how whatever comes out of this pipeline expects for bindings to happen. And they give you, they give you 2 options, basically. Either you lay out all of your bindings into one giant argument buffer, or this other solution that we went with, which is a bit slower because it goes through a double indirection, but it offers a bit more flexibility. So what we do is we actually use embedded root signatures into our shader code, and that maps out a top-level argument buffer, which just points to some other buffers that would be the equivalent of descriptor tables in DirectX. We also use reflection from both Metal Shader Converter and from DXC. is something we would like to see improve in the Apple tooling. Metal shader converter gives us all of the necessary information to actually dispatch the draw calls, but information about the resources themselves is not really available, especially if you're using this binding model. So we need to do that through DXC. We allocate all of these from a single metal buffer per frame, just to cut up on the cost of allocations. And we try to go about it in a way that kind of minimizes the amount of state changes that happens, just so we reduce the CPU work. So we have bindings that change maybe just once per camera or once per render pass, or some that are per draw call. We also have the separation between shader stages. And this comes in a bit handy because we can do some little tricks due to our allocation strategy. So you can see we put our tessellation stuff right at the end. And that means that if we have draw calls that don't have tessellation, actually in memory, those can alias, right? So the start of the second draw call can just overlap the tessellation that doesn't exist. This is, I keep pressing back. This is a high-level overview of how it looks like, a bit zoomed out. So one allocation per frame for the top-level argument buffer, and then the descriptor tables. The descriptor tables themselves cell in there is basically 3 UN64s. This is what Apple require. The information there is either an address to a buffer or a texture or sampler ID and some metadata on top. Now, some fun things about using this model is Metal is way more restrictive than other languages, as we found out. So while in other places you could just declare something and not bind anything to it and be happy, the validation layers on Metal will yell at you quite a lot. And not only that, you actually need to be really specific. So for instance, if it's a 3D texture, not a 2D texture, it will complain about that as well. So you do need some sort of reflection to make this work. The same goes with out-of-bounds reads and writes. You cannot expect those to give you zeros or to discard. So we did a lot of tightening up of our shader code just to make the validation shut up. Other things is if you're using version prior to version 3 of Metal Shader Converter, they have this thing where they require all of your texture binds to be array views due to some compatibility between HLSL and MSL. So that's quite annoying if you have, our engine is very DirectX 12 style, so you have the resource as a thing, and then you can pretty cheaply create views, RTVs, SRVs, UAVs. The views in Metal are not that cheap. So we did a bunch of optimization here just to check when we have to do these things. Do we actually need to create a view, or can we just use the Metal texture? That's the resource underlying all of this. Another thing they offer is this runtime header library, just to help you do the bindings a bit more easily. We do not necessarily recommend doing that if you have a larger project, because we found out that it does a bit of redundant work. So whenever you have heavy loads, it can actually start to affect your CPU times, but you can give it a try. And also you can opt out of this argument buffer, Metal buffer allocation style, and just provide the data inline using the set bytes stuff on the command buffer directly. But this is a bit tricky because it kind of ties your memory to the command buffer, which in the Metal driver are pooled together, so you can run into some issues there. But if you have a small project, you can go ahead. And yeah, Peter?
Yes, so this morning there was a bit of talk on render passes already, but I want to give it a little bit of a TLDR on TBDR. And so TBDR stands for tile-based deferred rendering, and it's kind of it's an architecture that's very popular in mobile GPUs. And it doesn't really relate to deferred rendering as you might know it from the software side of things. It's more of it's a hardware optimization that is used to reduce the amount of bandwidth that you need to render. And so, short overview of just kind of how it works is that the GPU will do this position-only vertex shading. So runs your vertex shader, but only outputting the position, does that automatically for you. And then writes all that into like a big shared buffer for the whole frame. And this happens for all draws that you have in the whole pass. And then after that point, the screen is then sliced into some tiles, and all of those triangles that you shaded the vertices for, you can then bin those into these tiles. And after that, you now have the ability to then go and work on each tile individually, so it can use this really fast local memory. And on Apple platforms, it looks a lot like it's just the same memory as LDS, right? So that's kind of the way to think about that. But that means that then it doesn't have to then write all this memory back to main memory all the time and spend all this bandwidth, which, like Mircea talked about, is really expensive in terms of your power budget. So that means Metal also has render passes. It doesn't have subpasses like in Vulkan, there's just render passes. But you still need to create them explicitly. And ideally, you would have a frame graph in your engine for this, because it is one of those things where you just really want to know kind of what's going to happen in the future. Unfortunately, not really a thing in Hitman, and it's just too much work to refactor the code base for that, because I mean, it is a live game. We don't want to touch too much stuff in the game that is running, and it's a lot of platforms to actually make it also work on then. So we ended up doing this, just create them on the fly thing instead. And it's kind of simple, crude approach. We just mark this 30-bit when we have our, it's a little bit like a DirectX style API we have for encoding this stuff on like our hardware abstraction. So when we change the render targets, then we just mark this bit, and then when we actually get to a draw, that's when we then compare what's in the render paths that we have going on right now, and where do we want to be at, and are they compatible? And I've kind of tried to draw it out a little bit, so like you can see, if you just did it eagerly and just made your render passes directly when you're changing your render target setup, then you might end up with some passes that don't actually have any draws in them that you don't need. Whereas if you do it lazily, then you get rid of that. It's like a poor man's frame graph. And then on top of that, we did some minimal changes in the high-level code to massage it a little bit to just get rid of some new render passes. Here I have tried to draw up a little example of something that could happen, which is like maybe you're binding your G buffer, and then you do a bunch of draws, and then you bind kind of extended G buffer essentially, and you do more draws. And that means that you now have two render passes, which means that all of your G buffer has to then go back to main memory and then get loaded back into the tile memory again for every tile, when it just added like an extra target. So the simple solution there is just go to your high-level code and then bind that extra target early, and then it kind of works out. Yeah, so pretty naive approach, but it actually ended up working a lot better than we were expecting in the beginning, I think. But it also helps that our high-level code is pretty well structured already for this, and the engine also already does a lot of sorting of draws into various buckets and all this stuff. But our load store actions are still quite conservative, and a load store action is like on a render pass. Then for every render target, you can kind of choose like, do I want to actually load something or store it back to main memory, or do I just want a cleared value, or actually do I not care about storing this back? And that can also be used for saving a lot of bandwidth. But most of the stores we have actually ends up being used, and for the load actions, when we're creating the render pass, we have a pretty good idea about should this texture be cleared or not. So that's like a typical mobile GPU trick that you don't do a clear explicitly. You just kind of, next time you load the thing as a render target, you can just say, hey, I actually just want this to be cleared, and then the GPU doesn't have to do any load. Yeah, and it also has compute passes. It's very similar to a render pass. It's just compute, but that also means it doesn't have any render targets. But it does expose these two different types of them in Metal. So it has the serial one, that's kind of this simpler one to get started with. And as the name suggests, it just runs them in serial. It just automatically puts a barrier in between each dispatch you do. But we have some passes, especially in our deferred shading, that it does this tile classification stuff where it'll operate on the same texture, but we know it's not going to conflict with each other. So those dispatches actually should run in parallel. And using this concurrent type of compute pass, you can do that instead, and then you can just put in barriers manually where you need them. And a kind of interesting detail in Metal is that when you, for example, you're in a compute pass and you put in a barrier, then that barrier only blocks stuff in the pass that you're in. So if you also started another compute pass or another render pass, then that stuff, even though it was kind of in the command buffer, was before, or even after actually, it's not going to be blocked by your barrier either. So all these passes, they always run concurrently, given the kind of, then you have some sync setup about when can the pass start. So that also means in theory, you can also just take your dispatch and put it in, like make a compute pass per dispatch, and then Metal will actually get a lot of parallelism out of that for you. But there's also a certain amount of driver overhead from that, and we were recommended to keep that low. So we just do this concurrent thing. And the way we then manage these barriers is also a fairly simple approach. We just have this fixed size buffer where we can store up to 32 resources that are needing a barrier. And then when we get to a dispatch, or if we've hit the limit of what we can store in this buffer, then we flush it, and Metal has this nice call that will let you batch, kind of do a memory barrier for all these resources, which will effectively then wait for the dispatches that you already dispatched that are touching those resources. So it's a bit on the conservative side. Could probably extract a bit more parallelism, but it ends up working out well enough. Yeah. And speaking a bit of command buffers, the way we handle those is we have a ring buffer of them, and then we kind of use this unwrapped index. You kind of imagine like that index is just this forever increasing uint64 value, and then when you actually need to access something in the ring buffer, that's when you wrap it. And that's kind of the synchronization primitive we use in the engine for when something on the CPU needs to wait for something on the GPU, which not all that often, but is also just used to make sure that the GPU doesn't get a hit too far. And we keep this to a maximum of 4 command buffers, because like Mircea was mentioning a little bit, Metal pools these things internally, and when you do draws on them or some of the things that might allocate some nifty memory on it, that stuff also kind of gets attached to that command buffer. And as usually happens when you pool stuff that has kind of dynamic memory allocation going on, eventually the things that you have in your pool, they will kind of trend towards all having like the max memory use of each of them. So keeping the amount of active command buffers down is a good idea when you're a bit tight on memory. On the GPU synchronization part, we started out just using the automatic hazard tracking, as it's called in Metal. So that's just where Metal will essentially take care of setting up all the barriers that you need between the passes, and you don't really have to worry about that. It does have a cost, and we were actually thinking we would like to do our own at some point, but there was just always bigger fish to fry, and it is a lot of work to move away from, because you kind of have to then actually do all of those barriers yourself. But it ended up good enough. We also had a go at implementing async compute and got it running, but we were a bit stumped at we weren't really seeing much of a performance gain from this, even though we do see that on other platforms with Hitman. And that relates a little bit to what I was talking about before, right, where the passes in Metal, they already run independently. So you actually don't really get much out of running stuff on an extra queue, because it's not really going to be blocking unless you literally, like, you can put in weights on the command buffer itself, but this automatic hazard tracking in Metal doesn't do that. So we ended up just shipping without the async compute at all. And then back to Mircea.
Yep, let's talk a bit about how we manage memory. So ideally, what you want is to not do a lot of allocations, right? Because they come with an overhead. So simple, just put everything in a single buffer and manage it yourself. The trouble with that is, like Peter mentioned, we're using automatic hazard tracking, which means if something within your pool of resources needs synchronization, that means a barrier for the pool itself. So then to work a bit around this, what we did is we split our allocations between things that are read-only and things that are potentially writable. Because read-only stuff is fairly simple, right? You just make it resident on the GPU, and then anybody can have at it. No synchronization needed. So for that, we mostly try to do these buffers that are either at the granularity of a per frame thing or persistent. And we try to put as much as we can in them. And with this, you kind of have to manage a bit fragmentation. But there are certain solutions out there, so we can recommend Sebastian Altanen's offset allocator or the original two-level segregated fit thing. They work pretty well. With writable, we chose to allocate them individually, again, to not run into these cases where we over-synchronize stuff. For our buffers, all of them are shared resources because it's a unified memory platform, so there's not a lot of benefit necessarily from having GPU-only visible thing or CPU visible-only thing, and it also cuts a bit on the total memory cost, because you just have one thing, you don't need to upload it separately and so on and so forth. On Metal side, we can also recommend using the set buffer offset method. Once you made something resident, if you just need to reference a new place within that buffer, this has a much lower cost. So abuse it as much as you can. For textures, kind of the same ideas go around. It's just that allocating a buffer as a backing store for a texture like you would do on DirectX 12 is not that great on Metal. We'll get to it in a bit. So then what we did is originally we tried to ship with Metal heaps. That was because we were targeting iOS 17 and residency sets are not a thing on that version. And with this, the only advice I kind of have is you need to balance a bit the number of heaps that you have. Because if you try to allocate everything from one single heap, then you need a lot of memory allocated up front. But the more heaps you have, then the more residency calls you need to do, so you're basically losing some of the advantages of using them at all. And also, if they're smaller, you're running into those memory issues with fragmentation a bit earlier. After we moved to iOS 18, we basically just allocate textures individually from the device itself and just handle residency with residency set, a single global residency set. And yes, for things that are created maybe on a per frame basis, we try to kind of pool those as well. So just to make sure that we don't keep allocating and deallocating stuff because it's slow. And again, specifically for Apple platforms, we recommend use resource stages variant to make your things resident to the GPU. The stages part is really important because it allows potential overlap between pixel and fragment stages within the GPU because you synchronize a bit more fixed. And of course, yeah, we're using basically a ring buffer to upload stuff just to pool them together, not have too many blit encoders and so on. A few more quirky things, Metal specific. It's really easy to lose lossless compression on your render targets. Going a bit previous with all of the view creation, a lot of the times if you have a naive approach, you would add this flag to your texture descriptor, and that one just disables lossless compression. So you need to check to see when you create a view if the pixel format that you use is the same, then actually, just use the underlying resource, don't create a view. And again, going back to linear textures, this is basically if you have a buffer backing store. I think in DirectX 12, it's something like placed resources. These don't really work that well in Metal. You cannot decide after the fact that you want to actually have a buffer version of your texture just to poke around into the pixel data. You need to know it in advance. And also, it kind of comes with these limitations. So you cannot have depth formats, you cannot have texture arrays, and you cannot have more than one MIP. So they're almost unusable. But yeah, moving forward, upscaling. Like it was talked already today, it's kind of a necessary evil. We don't really want to use it, but the resolutions on modern phones is fairly high. So if you want to run these big titles, you need to, at some level, find some wins. And for this, we chose Apple's own upscaling techniques, metal effect, spatial, and temporal. What I'll say is the screens are very small, and the DPI is super high, so the physical footprint of your pixel is really small. If you have details that are pixel level in your geometry or textures, is really hard to notice, and especially in motion. These were fairly simple to implement. There's not a lot to say about them. I wrote some notes there. So for spatial upscaler, we tend to see that it kind of over-sharpens a bit the image. And with temporal, if your scaling factor is very low, then the image becomes kind of soft. I'll show you some examples in a second. Just the final note is, of course, we want to render UI after upscaling just to have the crisp visuals. So here's a shot without, there is upscaling going, but none of the metal techniques. It's basically just upscaling as part of our own TAA pass. And then this would be with spatial. I'm not sure if you can see the details. They're pretty similar. It's, again, just a bit of over-sharpening. And then you'll see the temporal next, which is much softer at half of native res. But if you bump it up to the quality version that we ship, which is 80%, it brings back that sharpness, and it actually looks pretty good. And finally, to talk about the elephant in the room, PSO caching. There's a lot to say here. Originally, we were targeting a solution that uses metal binary archives, which is the preferred way of doing this sort of stuff on metal platforms. We ran into a lot of problems due to using metal shader converter and basically transpiling our shaders on Windows and delivering them through the resource server to the runtime and all of that. We wrote a bunch of offline tools to kind of finesse this and make it work, but at the end of the day, there was some Apple-provided tools that are supposed to take your IR plus your description of your PSO and then retarget that for other GPUs so we can ship. And that seemed to fail. So after a bit of back and forth with the guys at Apple, they said, until the ecosystem matures a bit around this metal shader converter, we should probably use something else. So we shipped classic shader prewarming, fairly straightforward. We basically run through the game, gather some information about the PSOs, save them in a binary format, and then at runtime, we leverage that data to create our PSOs. The intermediary states, such as input layouts, raster states, so on, those get created and pooled whenever the engine launches, and then the actual PSOs themselves get created on a per-level basis whenever the level itself loads. And we use sort of like this for a hash key. For our PSOs, it's just the IDs of the components from the pools themselves. And yeah, Peter.
Yes. So, I mean, you saw the video before, but this is a frame from the game running on an iPhone 16 Pro. This is the Paris level, which is the first kind of big level you get to after you've played the tutorial. And here I've then taken a capture in Xcode, and there's a lot of stuff going on in this screenshot, but I'll just point out some things here and there. So you can see that here on this one, it ended up at 17.5 milliseconds, which is pretty good out of the 33 milliseconds budget you would have for 30 hertz. But like I've been talked a bit about already, like these phones, they need some time to cool down because they are passively cooled. So you cannot just max out your budget. And also, when you do a capture in Xcode, then this profiling stuff you get in here, it actually clogs up the GPU, so you don't get this downclocking thing that I talked about, because that makes it really hard sometimes to see your performance improvements. But you can also see maybe that next to vertices, it says 7 million, and that's quite a lot, especially considering the resolution that these phones are then actually rendering at. So let's just say there's plenty of vertices to go around for each pixel. But we didn't really have LODs to scale down lower, and it ended up actually being good enough. But you can maybe also tell like this highlighted blue blob in the timeline over here. That's the vertex stage running, and there's a lot of it. And one of the tips we got from Apple was actually that even though you want to watch out for that bandwidth and all this, there's a trick you can do, which is if you have a lot of vertex shading, you can also then deliberately split up your path at some point in the middle, because then you can see that highlighted green blob in the timeline then actually ends up overlapping the next blue one. So then you can actually have your fragment shading from the first part of the stage then actually run in parallel with the vertex shading from the other part of it. And that just gives you back a lot of parallelism and can help you with then actually fully saturating the GPU. So even though it costs you some bandwidth and some power, then you can maybe gain a bit back, and it also just, it helps you finish your frame faster, so then there's more time for the GPU to cool down afterwards. Yeah, and now we just have a little bit of what we call the rapid fire. It's just a bunch of tips that we would like to maybe have when we started this thing out. I already talked a bit about this aggressive downclocking, right? But it makes it really hard to see your performance improvements, and it makes it really hard to do dynamic resolution scaling when you can't really trust your timing measurements that you're making in engine. So we tried implementing it, didn't really work out. We just ended up in this downward spiral where we always ended up just running at the lowest resolution bucket we have, but with the frame taking the full 33 milliseconds, because the GPU is just like, hey, I have plenty of time, I can just clock down a bit. And then you never get up again because you never have, you never have headroom enough for the engine to think it can go up to a higher resolution bucket. But yeah, so when the GPU does clock down, then it can actually then spend a bit more power on the CPU side, or at least just the CPU maybe has some more thermal headroom. So when you're doing performance improvements, kind of need to have a bit of a holistic approach to it sometimes, where you might optimize something on GPU, but that actually ends up saving your CPU because now that has more power budget to play with. And yeah, I already talked a bit about limiting the total amount of command buffers you keep around, but you also really want to limit how many you dispatch per frame, because Missile does have a bit of a big cost for each of these, especially when you're using the automatic hazard tracking. So there's just a certain driver cost with each dispatch, and the recommendation is to keep it a bit low. We just have the two that I talked about with the early and late. Make sure you use instruments. That's Apple's native profiling tool. It's really good for drilling down deep into functions, and it can do typical stuff like a flame graph and this kind of stuff. In addition to that, we actually also have this thing called a microprofile, which is our own profiler for that we use for the engine across various platforms. That's kind of better for the kind of mid-level things in terms of profiling. I showed you a bit of the Missile frame capture before. Generally just high recommendations for using it and getting familiar with it early. It's really good, and it can even do stuff like like you can debug your shaders and all this stuff. And it also is good for visualizing kind of where do you have data dependencies and all that. Then a bit back to the CPU side. You really want to make sure on these mobile devices that you don't do spin locks, because it just consumes power and battery, and the OS might just end up giving that thread more priority because it might think, hey, something intense is going on here. And then that, grabs thermal budget that you would actually like to use elsewhere. But at the same time, you need to not sleep your threads, because then you can end up in this situation where the OS deprioritizes your thread, and it also does this thing where it kind of, if you have a bunch of sleeps, then for the wake up, it might try to be like, all of these are within, certain amount of milliseconds. We can just, postpone some of them a little bit and bunch them together so we don't have to do more wake-ups than necessary. But that also means then you can get some big wake-up delays sometimes. So the thing to do there is just generally, when your thread needs to pause a bit, then do it on like some sort of condition variable, or like wait on some other thread to wake you up instead. Something to watch out for is the cost of clearing memory. We were a bit surprised at how big of a gain we got out of this, but in our allocators for the Metal backend, we initially, I think, or maybe it was added for some debugging at some point, but we just like cleared memory to 0 when allocating, just to keep it safe. But the engine doesn't actually need it, and we noticed it when profiling the game towards the end, and it was taking up actually, I think, a good 10-15% of the frame on the CPU side. So just not clearing that was a really easy performance win. Then in Objective-C, and when you're interacting with Metal, we use this Metal CPP, but even if you're doing that, you're still interacting with Objective-C. And it has this concept of auto-release, which is like a deferred release of an object. But that means that then that object is gonna stick around until that release actually happens. And typically, you can technically control it yourself, but typically you will have one of these releases only happening once per frame. So then you can actually end up accumulating a lot of memory that you could release way earlier, and then it just eats into your memory budget. And also, speaking of Objective-C, it has this memory management policy. It's pretty simple, actually. You can just Google this memory management policy thing. It's just naming based, but it's very well adhered to. Something interesting we also ran into while profiling was that our engine needs to be able to say like how much time passed, and it doesn't need it to increment while the system is sleeping. But if you're using this clock monotonic thing, that will actually do that. And then we were a bit surprised to see in the profiler that it actually goes and queries the time of day and all this stuff with the OS, which is pretty expensive. So just switching that to this uptime raw thing, which just doesn't do that, was again like a good, I think, almost 10% increase on the CPU side. Metal also has a lot of stuff where you can put in debug information for yourself to make your life easier. You can do these debug groups, and you can put them on with the command buffers and the command encoders. And command encoder is just like an encoder is one-to-one with a pass. But again, it's one of those things where knowing the future when you're actually doing these things is very beneficial, and since we don't have a frame graph. So we ended up just putting the first 2 levels of our debug groups on the command buffer, and then the rest in passes, and sometimes it looks a bit janky, but for the most part it's good. And then at last, just a little shout out for doing thin LTO. Thin LTO is this feature that is in Clang, where it's like your regular LTO, where you get optimization across your compilation units, but it's much faster because it can actually do the compilation in some very big parallel steps, and also it has much better incremental compile times. And so we tried enabling it with this, just add this LTO equals thin to your compile command, and it actually didn't add too much time compared to our compiles without it, and it was a huge performance difference. And especially because usually in the code base we have these Unity builds where you'll chunk up a bunch of the compilation units together to kind of that gives you like a little bit of that LTO stuff, but we didn't have that working for the iOS platform. So this thin LTO was really critical, especially when you're doing profiling and you want to make a change and you want to see quickly does it actually make a difference. And just with the way our code is structured, we absolutely need that. And we've arrived at the end. So concluding a bit, we ended up shipping the game, and it runs at 30 FPS, and you need a iPhone 15 Pro and newer. So you can enjoy the World of Assassination on your phone. It's the same game as you have running on a console, for example. And overall, it was a really fun project to work on, actually. It's a good, healthy dose of pain, but many really interesting technical challenges to do here, and we learned a ton of things by doing this thing ourselves. So, thank you to...